Recording here. Welcome to another exciting biomedical signal processing class. In this class, what we're going to do is review the Radix2 FFT. And so my first question is, what's it mean when it's Radix2? Mike, what is Radix2 mean?
Dividing the numbers basically in half, splitting off even and odd.
Radix2 means it's using base 2, which means it has to be an integral power of 2 in length. You can have, I think what you can do is you can make a claim that fast Fourier transform is not one algorithm. Fast Fourier transform is a class of algorithms, and you can do Radix 2, you can do 4 at a time, you can do prime factor algorithms, you can do decimation in time, you can do decimation in frequency, you can do Hartley transforms, which are variants on the fast Fourier transform. You can do a whole bunch of different things with integer fast Fourier transforms and floating point fast Fourier transforms. There's one thing that came out of MIT called the fastest Fourier transform in the West, FFT W, right? And then, you know, everybody's got their own sort of thing about how to optimize for Arduino when you want to go and make things run fast there. And some people use assembler, and they'll give you a library, and it's just totally tight. And, you know, what you guys have been doing is you've been coming up with your own implementation, and I think that's very educational and very fine. And it's nice because you get a chance to sort of benchmark your implementation against the professionals and just see how much better or worse you are. And then there are other questions like, do you want to use double precision numbers? Would you be better off with floats instead of doubles? Those are trading off, you know, precision for space. And someone said, well, after I got 2 to the 6 samples, I was done. You know, I couldn't do any more than that. And I said, well, you know, you only have, and I'll do the computation here, 1024 bytes of RAM, right? Isn't that about the limit for the Arduino Uno? So that's assuming you don't go into the double EEPROM. So if you figure it that way, 64, well, I guess we can do it with Excel. 64 samples times 64 bits per sample times 2 because it's a complex number divided by 8 because you want to get it in bytes comes to something like 1024. So that's your limit right there. You don't really expect to do a whole bunch more than 64 samples at a shot. You know, that's it. So then I thought, well, let's try and do some benchmarking and see what our sample rate will be as a function of the total size of the window in the fast Fourier transform. So I sat here and I started a little Excel spreadsheet. It's fun, right? And I said, well, if I do 64 elements, how long does it take? And it says 21 milliseconds. So then I said, I wonder what the sample rate is on that. So I figured the sample rate on a 21 millisecond window, and then I multiplied by 64 because n, the number of samples, was 64. And then I did the same thing for 32 samples and 16 samples, and turns out overhead starts to dominate at 16 samples. So your sample rate could actually go down as the number of samples you do at a time decreases. So here's the code that I got from Rich. And what we'll do is we'll set n to be something like 3, right? So now n is like 8, 2 to the 3, which is 8 samples long. And we'll do a run. And what do we get? 8 samples takes 2 milliseconds. So if I plug that in, here comes 8 samples. The number of milliseconds is 2. And now let's figure out your sample rate. And it comes out to, well, 4K samples per second. That's pretty good, actually. And now, if your window gets really small, I said 2. So now that's 2 to the 2. That's 4 samples instead of 8 samples. I don't know if that makes a whole bunch of sense, but you should be able to compare that to a DFT. And he says he can do the 4 samples in 1 millisecond. Now that's the same sample rate as 8 samples. So it's clearly superior when running at 8 samples than it is at 4 samples, I think. But there's latency involved. But the latency is not so bad. There may be other issues involved too. Is the millisecond measure correct? When you get down to under a millisecond, it's probably just going to round it up to a whole millisecond. And if that's the case, then this could be running in microseconds. So you don't really know. When you do a sample for benchmarking and it gets that small, and you only have the ability to measure to the nearest millisecond, you really don't know how fast this ran. You really can't tell. That's interesting, isn't it? Yes, Professor Lyon. Very interesting. Okay. So then here comes my my DFT. And I thought it would be fun to benchmark the DFT. But I had a lot of trouble doing that. And I really kind of wasn't sure why. Let's go back and take a look at the FFT and see what Rich did. So here's a bunch of, I'll call them global variables. And these were being allocated and set, but not part of the setup. And then I see what you've done here, Rich. You got a delay. Now, what's up with this delay? I see what you've written.
So when you hit the serial monitor, it actually restarts the code. So just to make sure that was as clean as possible, I just put it right there.
It restarts the code?
When you hit the serial monitor button, it reruns the code. Like it cuts it off wherever it is.
Oh. And does anybody know how to slow down the scrolling when you click on the mouse? Yeah, I know I tried. Just thought I'd ask again for no reason. Thought maybe people got smarter or something. I didn't get smarter. I never figured that out. So I'll put that in there. Maybe that's what was going on.
I have my DFT benchmark.
Oh, you have a DFT benchmark? Where's that at?
The DFT we did last time, I have mine. DFT benchmark.
Is that part of the benchmarks that you ran? So where do I find that? Oh, well, maybe the thing to do is just to see if I can benchmark it with what I've got. So here's the ramp, and I guess that's going to do a print. Then he does start in milliseconds, captures the elapsed time. And now at this point he's still in the setup, you know. But what I'm thinking is that it might be possible to print out your benchmark here. So I thought it might be fun to just sort of run the DFT and see if benchmark gets emitted. So the benchmark gets emitted. It looks like it's printing something else. Oh, it's printing out the serial ramp. I guess that's okay. So now let's print out the elapsed time. And see if that works. So we're benchmarking the DFT. Now he says the elapsed time is infinity. So what could be the problem here? Any ideas? Start time can't be infinity, can it? I mean that's kind of weird, right? Shouldn't it be like 0 or something? Millis, that's how you get it, right? So what if I just write out start time? Is start like a keyword? Is that why it's having a problem? I really don't understand this. Start time should be like a number. See, it didn't even print out start. What's up with that? Is it possible it doesn't know how to concatenate strings? I'm thinking there's something about this C compiler I'm not understanding. You can't do the plus sign. I think that's what it is. I'm too much of a Java programmer. Oh yeah, it's working now. So start time is 3002 milliseconds. So let's do this. We'll change start time to elapsed time. And we'll take start time and replace it with elapsed. And that should help us get some kind of a reasonable number out of the darn thing, right? (17 milliseconds). That's slow, right? Let's compare that now. We were just doing what, like 8 samples? So what we'll do here is we'll start up another thing. We'll do n milliseconds, and then we'll do a sample rate, and n was 8 samples, took 17 milliseconds. And so if we use the same formula here, that doesn't seem right. Is that right? Yeah. Yes, it is. Odd that it should take so long. Let's try that DFT again. I don't like this 3-second delay, so I'm going to change it a little bit. Oh no, that's yours. Let me get to my code. So what are we using for n around here? 8. Yeah, that was 8 samples. Let's try it with 4 samples. It doesn't seem to be any faster. It's ran in 4 milliseconds. So I cut the number of samples in half. Oh, actually, that's quite a bit faster. Copy, paste, but it's quite a bit slower than FFTs. DFTs are slow. I don't think there's much choice. I mean, you have 4. I mean, there's nothing wrong with doing 4 samples, but if you have 4 LEDs and they're supposed to represent 4 subbands, then you probably want 8 samples. And according to this, I can run the 8 samples in only 2 milliseconds with the FFT instead of running them in 17 milliseconds. Now, just out of curiosity, I'd like to see the quadratic increase with the DFT. So let's go from 8 samples to 16 samples and see what happens to our time. And I'd like to change my delay over in here to 2 seconds and see if we can't get things to run a little bit faster. So he says 70 milliseconds for 16 samples. And he's giving me some kind of wacky stuff here for output. I think I ran out of space. $70 milliseconds for 16 samples. A stinking eternity, really. Really slow. It cut my sample rate in half on a per sample basis. Now I'm not sure, but I think I should be able to do 32 samples with a DFT. And I'm wondering if I should just take some of these print statements out of here, because I think they might be slowing me down, and I'm not sure. I always worry about print statements slowing me down. 279 milliseconds for 32 samples. How about that? So there's that quadratic thing happening now. Now you can really see what's going on. Sample rate 114 milliseconds per sample. Does that seem right to you? No, 114 hertz. That's what that is, 114 hertz. And now let's go up a little bit more. I think our N got all the way up to 64 for the FFT. And that's 1,124 milliseconds for 64 samples. 1,124 milliseconds for 64 samples, giving me a sample rate of 56 hertz. Wow. Wow. So now you get a sense of why people use the FFT instead of the DFT. Clearly there was an issue here, right? And we could try and address this issue in any one of a number of ways. What could we do to make this FFT a little bit faster? Well, the FFT is already faster than the DFT. Seems like we have a fundamentally faster algorithm with the FFT. What would be another thing we could do to make the FFT faster? Our FFT is it, let me ask you another question, maybe a more pertinent question. Is it fast enough to keep up with our audio rates? No, right? Because our audio rates are 8 kilohertz. And this FFT on our little Arduino, our little 16 megahertz toaster controller, is only pulling out what, like 4 kilohertz. So our maximum frequency for response will be how fast? Come on, guys. Right? So it's got to be like 2 kilohertz. That's not a particularly good sample rate. So what can we do to improve matters? Could do a different algorithm. Do you think maybe single precision floating point would be sufficient for our application? Why not? Right? Why not? So how hard would it be to go from single precision to double precision floating point, I wonder? I'll bet Rich could do it. I'll bet he's almost finished now. So Rich, here's your code.
Most of my stuff is called up at the top.
Yeah, I mean, can this, what do they call it when it's single precision? Isn't it called float? So if I switch this to float, does the compiler complain? No, he just likes it. He says he doesn't care. So anything else?
There's a couple inside the actual algorithm.
I mean, I'm liking this solution because double precision stuff is taking up so much space that we can hardly increase our window size any. So that's not too bad. I mean, if anything, it'll improve by a small constant quantity, right? So let's see if that works. Oh, printing arrays is probably not going to work good if it's wanting to take double precision numbers, but that's okay. We don't need to print arrays, do we? What about these FFT arguments? Oh, they're all wanting to take doubles? What else? Where's this print array stuff defined? It's the last one? Oh, there you go. Let's just make that float. And that's all good. Well, that's an easy hack. They should all be so easy. Uh-oh. What's up with that? Serial port COM already in use. Try quitting other programs. Here. Yes, no, yes, no, yes, yes, no, yes. Okay, let's see what we got here. Your code prints too much. Yeah, I see that. So now it says 64 samples ran in 21 milliseconds. Now, that's kind of where we were. Is it possible that your code is like slowing us down because it's just printing a lot? No?
No, because I take the times before and after and I set these in phone.
You're right. So I did nothing to improve matters at all. Really nothing. What about the size of the array? Can we at least go beyond like 64 samples? What if we went to like 128 samples? Oh. Yeah, this is bad. It just died. It can't find the space for that. Let's reset back to 6 and run this again. And where are we? Yeah, now it's back. So Bottom line, changing the number of bits in the computation from double to float did almost nothing, practically nothing, to the algorithm's performance. So I loved the idea. My hypothesis was that it would work. The data which I gathered shows that it didn't at all, and that my hypothesis was all wrong. So what do I do about this? I'm trying to get a better algorithm, right, for doing my pitch detection.
One thing that you probably do.
Tell me.
Inside of the FFT subsystem,
Mm-hmm.
there's a copy for loop that copies the input parameters into the nodes, like that for loop. So if you didn't do that,
Yeah, you're not doing an in-place FFT.
yeah, you could probably do it on the existing one.
Yeah, there's no reason why you should make that copy. But how long does it take to copy 64 numbers? Or 128 numbers? It shouldn't be that long.
I mean, that's probably the longest thing. And then there's another, the bit reversal one that I got in your code.
Mm-hmm.
Supported in there too.
Well, that's not a copy loop, though. That's a... Well, it's kind of a copy loop because you're doing a bit reversal and you're using a temp array. And these temporary variables, are they considered global? You're not reallocating them each time.
Just the first time you call it.
How come you keep recomputing 1 to the m or 2 to the m? Can't you compute that just once? M doesn't change, right?
Well, it's inside the for loop, so yeah,
That should be outside the for loop, shouldn't it?
that was direct copy from Java.
Well, I know, but I mean, hey,
M is the loop variable, so it just changes.
m is changing. Yes, yes, yes. Okay. No, that's efficient. I see nothing really wrong with anything that you've done here. It's all very fine. So what I would do is look for a better computation. So one thing that I thought was interesting was the Hartley transform. Now, have you all heard of the Hartley transform? With the Hartley transform, you don't need to do any complex number calculations. And it was firstly described and patented by a guy named Bracewell. And what you do is you use cosines and sines just like you do in the Fourier transform. But you don't need to have any... here, get it up here. There. Cas is cosine of t plus sine of t instead of cosine of t plus I sine of t. So it's not a complex number. A lot of times I think what happens with the FFT is we lose sight of the fact that internally the FFT requires that we store everything as a complex number. And that doubles the amount of storage that we need. And that's kind of a bummer. But the other part of all of that is that doing complex numeric multiplication is a little bit more cumbersome, right? And you can see complex multiplication taking a little bit longer because you have to create these auxiliary variables. I'll show you what I mean. This here, that's a complex number computation. How can I tell? Well, it's like this. If z equals a times b, where z, a, and b are complex, then the way you would write that is z equals the real part of a, let's call it RA, plus the imaginary part of a, let's call it IA, or maybe we should call it AR. AR plus AI times BR times, plus BI. Right? So in terms of complex numbers, if you cross multiply, Z is equal to AR BR plus AR BI plus AI BR plus AI BI. Right? So that's just multiplying the external parts of the parentheses through association. So now if I gather the like terms, I say the real part is AR times BR minus, and now the reason I say minus is because I have AI times BI, and they're both imaginary, and I times I is minus 1, so that's minus the AI BI is minus A times B, the real part. I'm not liking my notation. There's got to be a better way to do this. I'll just write the imaginary part of A plus, no, times the imaginary part of B. And now for the imaginary part, it'll be AR BI and BR times AI. So that means I've got to gather a temporary variable for the imaginary part and the real part in order to be able to store it and do the multiplication. Another way you can do it is you can express it in polar coordinates. You could say Z equals, let's call it A times B, and that's equal to AR E to the I theta, let's call it A, or A to the theta, and then you can have times BR times EXP. Geez, notation's a real battle when you're typing it like this. I to the phi. And so then when you're done, what you'll get is Z equal to AR times BR times EXP of I to the theta plus phi. Because with a like base, the law of exponents requires that the exponents will add. So what this basically says is that e to the I theta times e to the I phi is equal to e to the I theta plus phi. Right? Exponents add when you multiply things that have a common base. Well, you don't have to do any of that with the Hartley transform. I like to call it sometimes the Bracewell transform, and it says it's Hartley, but Bracewell wrote so many books about it that people have started to call it the Bracewell transform, and it was 40 years after Hartley first devised it. So I like this transform. I mean, this is a good one, right? Because check it out. No complex numbers at all. That's pretty sweet. Not only that, but you don't need an extra array, right? That whole extra array with the reals and the imaginaries and then the copying that you did. None of that's needed at all. This can all be done in place. And for the inverse transform, you can use the same exact code, just like the FFT, done twice. And then, if you want, you can relate it back to the Fourier transform. Now, if you take a look at what's going on here, it's kind of looking like a complex conjugate with a difference. And the difference is how they're reflecting the transform about the center. So that's a little wacky. It makes filter design more complicated. It's not a direct convolution. Here's the convolution. Here's how it's defined with Hartley. And you can see there's all this extra cruft coming in when you try and do a convolution. That's not good. Let's see what else you got. Nothing's for nothing, right? I gotta say, I'm not unhappy with the Hartley transform, but I've never really used it for a whole lot, and I couldn't really figure out why I'd want it. I got a bunch of transforms. You want transforms, I got transforms. So here's one. Hartley transform. And this is the one-dimensional discrete Hartley transform. Looks like I'm going 3 elements at a time here too. So I'm really trying to speed things up with optimization. So this is a 64 element Hartley transform. I think you can just run it. Oh, I'm looking to do a little compile. Oh, yep, there it goes. Elapsed time 114 milliseconds. That's pretty good. Now, as part of the big benchmarking thing, might be really good to see how that compares with the with the Arduino. How much effort would it take to port the discrete Hartley transform over to the Arduino, I wonder? It's not all that much more code than the what do we call it? The FFT, but is it worth it? Right? That's a big question. Is it worth it? Right? It's got all these problems, not the least of which is it doesn't afford you a direct convolution. So the answer is, yeah, maybe it's worth it. Kind of depends on what you want to do. Here's a slow DHT. It hasn't been optimized the way the prior one was. And looks like it's set up for 16 and 22 milliseconds. What was the other one? 117 for 64 milliseconds. Let's change this to 64 and see how fast it runs. Actually, that's pretty fast. I think this slow one is faster than the fast one, oddly enough. So my simple discrete Hartley transform uses the CAS function. The CAS function is the same exact function that was described in the wiki page. I don't know if you noticed, in the wiki page they have this thing in here called CAS. It's in here somewhere. There it is. It's cosine of t plus sine of t. Now there's an identity that can make that a little bit faster. I don't know if you saw that in there, but the identity says if you've got the square root of 2 hanging about, and of course you can pre-compute that, then you can multiply it by the sine of t plus pi on 4. Whether or not that's going to afford you even a millisecond of improvement, I don't know. Right? All you've done is you've obviated the need to compute a cosine in advance. And in fact, if that's what you wanted to do, you might as well have just made a table and done a lookup. I mean, that's always possible. So you can trade space for time in that way. You know, after a while it becomes bit diddling. What else can we do? I mean, that's a nice way to go. Change the transform, right? Discrete Hartley transform, that's a perfectly good transform. And they call it slow. But it's not so slow. And at 17 milliseconds, how did that compare with our Arduino? Comparable. How about that? Comparable. Of course, the Arduino was written in C, and we're writing in Java. If we took the code and rewrote it for Arduino, I don't know, how hard would it be to do this? You guys up for that? Yeah? You're up for anything? So, what else can we do to make things go a little faster? Here's a fast... This one says fast 1D DHT working. How much faster could this be, I wonder? Is that the one we just tried? This is a different one. I don't know what this is doing. I forgot. Oh wow, that was 256 samples. I'd have to do a I have to capture the time. Long start equals system dot current time in milliseconds. Do a fast forward discrete Hartley transform in 1D long let's see, we'll call it EPS for elapsed time equals system dot current time in milliseconds minus the start time, and then just for good times, let's print out the time. Elapsed time for the whole process was n quote plus EPS, and we ought to print out n as well. So quote n, or I guess capital N, n quote, equals n quote plus n plus quote, there. Let's just try that. This didn't print anything. Oh, I should have run the demo. Well, I don't know what I'm running then. Here, we'll just run the demo. And see what that does for us. That demo did an awful lot of printing. Elapsed time 2 milliseconds for a 256 element. Man, that sounds fast. 2 milliseconds. Huh?
So there was no complex number.
Don't need any complex numbers for a discrete Hartley transform. Huh?
Should be fast.
Well, yeah, but I mean, gee, that was really fast. I got ramp data. And then I ran this. What does this do? Now, this is doing a lot of work. Well, one thing I would say is that if you can find a really fast algorithm and it does what you want, you should go for it, because a better algorithm is always going to be a big win. And when you're on a small computer like the Arduino, speed matters. You really feel it. You know, if you can do 256 samples in 2 milliseconds, I'll just give you a feel for that. 256 samples in 2 milliseconds, that's 128 kilohertz. That's blazing. That's faster than your A to D converter. That's great if you can do it. So I'm liking that. That's a really good one. So what say you? This is looking like very straightforward code to me. It's called the in-place fast Hartley transform. Converted to C from BASIC in the Bracewell book. The patent on this transform dates back from the early 80s, so it's way out of patent. Patents only last 20 years. If there was ever any reason, you know, to care about the patent. All of these local variables could be global for your how you say, your little Arduino program, right? What else? It's got a lot of auxiliary variables. I'm liking this idea. I'm thinking this is something you guys really ought to think about. I did this back in 2008, old, right? So let's copy that, and let's go into Blackboard and devise an assignment. Is this homework 9? Okay, homework 10. This is the Hartley transform, and let me see now. Using the example given in Fast 1D discrete Hartley transform working, which is in the package known as Math Hartley Transforms, in the package Math Hartley Transforms, derive an implementation on the Arduino Uno, benchmark what are we using for a benchmark now? Copy. N for values, paste. So N for values 64, 32, 16, 8, and 4. And then what else? Can you run higher values for N? That's a big question, right? Because what's the upside of using the Hartley transform other than the fact that it looks blazingly faster than the discrete Fourier transform and quite a bit faster than the fast Fourier transform? No complex numbers, right? Remember, no complex numbers are needed for the DHT. Wow, what a win. How cool. Sweet, right? So, is it good to use a discrete Hartley transform because you're not getting the same capability of doing a convolution? And the answer is yes, because if what you want is a simple display of the power spectral density, then maybe you don't need complex numbers, because remember, the first thing you do to get the power spectral density is you're squaring up the real and the imaginary parts anyways. So if you're going to square them all up, you're going to get rid of all the complex parts, and if all you want to do is light up LEDs, well, who cares about the complex parts? Really? What difference can it make? You're just going to make a simple output, and you want to see sort of what the spectrum looks like, so there it is. You got a nice way to quantize the spectrum. You got problem doing convolutions, but that wasn't really what you wanted to do anyway. So what up? This is a perfectly valid thing to be doing. You should do your benchmark against the following results. Okay? And what I'll do is I'll just give you my results. Your mileage may vary. That's what they say, right? So now you've got, my results as I did them here in class, and you can come up with your own sort of table and You know, this is one of those things where you're using the computer to explore algorithms. That kind of feels like science, right? It should. That's sort of what scientists do, kind of, sort of. Right? Computer scientists use computers to explore algorithms the same way astronomers use telescopes to explore the heavens. And that can be worth up to 100 points. And allow multiple attempts. And due dates. Due next week. Hey, when's this class over? The final's on the 16th?
The last class is the last.
I thought I had 2 classes left.
Yeah, you do.
So is the final on the 23rd? That seems a little late.
No. The last day of classes is the 11th.
Not for this course. This course goes to the 16th.
Does this course go to the 16th?
So that would be the final.
I say we should. That's when we should do it.
Well, if we're doing the final on the 16th, then I think maybe we're going to have to devise an extra. I mean, I don't see anything wrong with making this due in a week, because this is just seeming routine engineering, and you guys will have no trouble doing this now, because you've already got good FFT experience. So let's hit submit on this. And now I think maybe we should take a little break. So I'm going to hit stop.